All right, first part of bonding. The Lewis model. If you've taken 3A or high school chemistry, you should remember vaguely the Lewis model. Hopefully you'll be able to pick it up quickly. I know that people have very different experiences with their high school chemistry though, so we'll see. One of the reasons that bonding models are important is that we use them in much more advanced fashion than we did in 1989, but you can use bonding theories and like simulations of elements and molecules and stuff to figure out how they might interact with things based on properties that we know about elements. So this is actually commonly part of the process, the pipeline for drug development companies. They'll come up with like, hey, this is a thing that we want to target. They'll figure out what the structure of that biological target is. What does it look like? Where's the important parts? And then they'll throw that into a simulation, have it wiggle around and stuff like it does in a body, and just throw 10,000, 100,000 different chemicals at it. What sort of things might fit into that little spot? And then they'll narrow down their list of 100 or 3,000 or 300,000 or however many chemicals it is. They'll narrow that down to maybe like 10,000 or 1,000. And then they can go through and sort that down further until they eventually end up with maybe like 50 or 100 chemicals that they actually want to try. And then they can pay researchers in their labs to go and try those things. So that's where this comes in. We're doing the very most basic level. We're not going to do any computer computations. We're just going to do pen and paper bonding models. So our bonding theories that we've talked about, or that we can learn about, I don't know if we've talked about them much, explain how atoms bond together to form molecules. Bonding theories can also predict why some molecules are stable and others are not stable. We can also predict the shape. Shape is actually a very important feature. It determines chemical and physical properties. There's a double space in there, that's annoying. And different bonding models have different utility, different benefits. So predictive power and complexity increases the more computationally intense your bonding model gets, but we don't really need to get there. Certainly not today. The one that we'll be focusing on is the Lewis model. This is the simplest model for making quick predictions. Super simple. You can do it on paper. You can learn how to do it in a couple of days. Some things that we're going to be predicting are shapes. Like, how are the atoms arranged? What does it look like? And stability. With the Lewis model, you could just shovel any number of atoms together and see if they'll bond. And if we can come up with a stable Lewis model, then maybe it could exist. In the Lewis model, our valence electrons are represented as dots. So a dot equals an electron. We have chemical bonds because they lower energy. They lower the potential energy between the particles that compose the atoms. Lower energy is more stable. Atoms and molecules don't have brains. They're just little globs of fundamental particles jiggling around, moving around, doing their own thing. They don't know any of this. They don't know that they're in a more stable configuration, It's just that they're shaking around, and if you shake it around long enough and it's stable, then the stable one is the one that'll stick around the longest, and so the things stay bonded together because that's more stable than not being bonded together. So they just kind of get stuck there energetically because it's the lower potential energy. When atoms approach each other, just traveling around like they do, the electrons are going to repel each other, the nuclei are going to repel each other, but the electrons in the nuclei are attracted to each other. Right, so for example, we could have these green dots that represent the nuclei. These two things are heading towards each other. As they head towards each other, these electrons on the right one might start getting attracted to the nuclei on the left one. The ones on the left might be attracted to the ones on the right, and they form a sort of molecule, if you will. So they might join forces and share their electrons. What we'll talk about first is ionic bonds. Metals tend to form cations. In case you forgot, cations are positively charged. Nonmetals tend to gain electrons. They form anions. So when metals and nonmetals interact with each other, they can do an electron transfer. So if this dot represents sodium's electron, sodium and fluorine might interact in this way. Sodium, fluorine are approaching each other. The sodium has this one electron in its valence shell, and fluorine really wants another electron, so fluorine takes sodium's electron. When that happens, we get a positively charged sodium, and we get a negatively charged fluoride. And since they're positive and negatively charged, they're attracted to each other. Covalent bonds, on the other hand, form generally between nonmetals. So when nonmetals interact, rather than completely giving away their electrons, they share some of their electrons. They both want the electrons. They don't want to lose any electrons. And so what ends up happening is they share. And the most stable way for them to share is by holding the electrons between them. So at the bottom here, we've got a couple of depictions of two nuclei trying to share an electron. And the hardest place for them to be is anywhere that's not right in the middle. When they're right in the middle, it's the easiest. They both have the most access. It's like if two people were pulling on a string. It's going to end up directly between two people rather than being way off here somewhere to the side. That's not going to last very long. Metals, on the other hand, can also bond. So metallic bonding occurs between, you guessed it, metal atoms. Metals tend to lose electrons easily. So you've got a bunch of people, or a bunch of electrons, or a bunch of metals, sorry, atoms, that are all like, we don't really care about these electrons. And so what happens is you get a commune. So the simplest model for the way that metals bond is the electron C model. You've got a big, like, flat layer, we can think of it, of metal atoms, and they all just kind of like donate their electrons, and there's a free-flowing exchange of electrons, and it's really cool, man. So that's one way that you can think of metals. I don't know why there's not like a diagram, because there's a diagram in my 3A slides for this. So these would be all of our metal centers. And these are all the electrons flying around. I think that this explanation makes a reasonable amount of sense because we typically think of electricity as like electrons flowing, and if this is what's happening, if this is what like our metals are like when you just have a bunch of metal atoms together, it makes sense that the electrons, that they would conduct electricity because we've got all these free-flowing electrons. They're not like stuck in place, and so they would be pretty easy to move relative to our covalent bonds where they're stuck between the atoms and they're not going to move very well. So just free-flowing electrons. So in our Lewis structures, we're going to represent valence electrons, our outermost electron shell, as dots. We've already talked about them before. So our Lewis symbol for oxygen, we write the symbol for oxygen, O. How many valence electrons does oxygen have? It forms a 2 negative charge when it's an ion. It's 6. It's in 6A or 16 for its group. So it has 6 valence electrons. So we represent those as dots. And the way that we put them in typically, it doesn't really matter which order you stick them in or where they go in particular, but we put them in singly first, as you saw me do, and then you can double them up after that. There's 4 sides going with the 4 cardinal directions, up, down, left, right. So we can get a maximum of 8 valence electrons, and I think this is on the next slide. Okay, dots placed with a maximum of 2 per side. Placed singly first, then doubled up. So if we had a completely full valence shell, like with neon, neon has 8 valence electrons, so it would have 2 on each side. And that's as many as you can get. And that's what we call an octet. The 8 for oct, like octopus, octagon. Octets are stable. For very small things like helium and hydrogen, a duet is also stable. So when we're doing Lewis structures, we're putting them together with the goal of getting octets on everything. Everything needs an octet, or at least should be as close as possible to having an octet. So every atom gets an octet. That's our guiding principle for Lewis structures. Questions so far? Cool. We can draw Lewis symbols for potassium and for chlorine. Potassium has symbol K. How many valence electrons does potassium have? 1. So we put 1 electron. I'm putting it on the right side because that's where I wanted to put it. You could put it up, down, or left as well. Chlorine has the symbol Cl. How many valence electrons does chlorine have? It has 7, and so we put 7. We put 4 first, and then we can double up after that. So it has 7 valence electrons, 7 dots. If we turn these into ions, potassium is happy to lose 1 electron. It can donate that to chlorine. When it does that, the thing that's happening with its electron configuration is we're stripping away that 4s1 electron. And secretly, what that means is we've revealed a complete and full octet. So in that way, it achieves a full octet. It wraps back around on the periodic table, becomes like argon. So we write it as K+. It doesn't have any valence electrons. We don't show those core electrons. For anions like chlorine, we would write this in as so. The colors are just so that you're keeping track of which electron came from where. And we have to put brackets. And then outside the brackets, we put that negative charge. The brackets show that these electrons are only on chlorine. Because the way that we would represent these bonding together is we would just plop our K+ right next to the left bracket of the chlorine. And it means something else if there's 2 dots between symbols. So for example, this is wrong. The reason this is wrong is because this means shared electrons. If we just put 2 dots between 2 symbols, that means they're sharing the electrons, which is not what's happening here, and so we use the brackets to make sure that it's clear they're not sharing. This is a one-sided arrangement. It's a 2-sided arrangement, but chlorine's holding the electrons. We can use Lewis symbols to predict the formulas for the compounds that form between magnesium and nitrogen. There's other ways that we can come up with the formula for the compound that forms between magnesium and nitrogen, but this is just to show you that it's got some utility for doing this. Magnesium has how many valence electrons? 2. I'll put 1 up, 1 right. How many does nitrogen have? Yeah, it has 5. Magnesium likes to give away electrons. It's a metal. Nitrogen likes to gain electrons. It's a nonmetal. What is our goal when we're putting together Lewis structures? It's octets. We want full octets. So if we give away both of these electrons from magnesium, what does that do for magnesium? Does it have a full octet? It does have a full octet because we stripped away its 3s2 electrons. That wraps it back around. It's got a neon configuration underneath. Okay, so magnesium's got its octet, and it's also a 2+ because we move those 2 electrons. What about nitrogen? Does nitrogen have an octet? It has 2, 4, 6, 7, not an octet. Where can we get another electron for nitrogen?
Another magnesium atom.
Yeah, that's right. We're going to pretend that there's another magnesium lying around. This magnesium also has 2 electrons in its valence shell, so it can donate one of those electrons. And now nitrogen, I'm just going to write the corner of the bracket, has an octet. Does our second magnesium have an octet? It does not. Where can we give away that last valence electron? That's right. It's another nitrogen. So there's our other nitrogen. A convenient place for this magnesium to give away its one remaining electron. And now that magnesium has a full octet. What about our newest nitrogen? Octet, no octet? Definitely no octet. How many electrons does it need? 2, and we can get those, yep, you guessed it, from another magnesium. And that magnesium has, just like the magnesiums before it, 2 electrons. So we give away both of those electrons. Magnesium's a 2+, and it's got its octet. What about that new nitrogen that we just brought in? Does it have a full octet? It sure does. Again, just drawing the corner of the bracket. Confirmed octet. So this predicts that we will have Mg3 N2. The way that I would have predicted it, we know what charge they're going to form as ions, and if we wanted to, we can crisscross it. Mg3N2. It's a little faster, but Lewis theory also shows us the same result. Questions so far? Great. We will pick up here in a bit.